All right, we're now going to do a beam analysis for a simple beam. This one has two equal concentrated loads and they're symmetric. And so these are the concentrated load. Each is 500 pounds and they're symmetrically placed or evenly placed along the beam. And so the first thing that we need to do is create our free body diagram. And so I'll come down here and I will sketch that out. So here's our beam. You're going to put one load on it right here, a concentrated load. That's equal to 500 pounds. Our other load will be here. Going to be load 2. Alright, our reaction forces now. Here we have a reaction force of A, reaction force at point A. We have a reaction force at B. We need to put in some dimensioning now. So to our first concentrated load, that distance is going to be 4 feet. Second concentrated load, again 4 feet. And our overall beam length is going to be 16 feet. Alright, so that takes care of our free body diagram for our beam. So the next thing we'll need to do is calculate, sum up the forces in the y direction. So we'll do that by using our formulas for equilibrium. And so the sum of the forces in the y have to be equal to 0. The forces in the y direction we have RA, reaction force at A, we have the reaction force at B, we have force at concentrated point 1 and it's going down. So I'm going to put minus 500 pounds for the direction of that one. And then we have this one here at point 2. It's minus another 500 pounds. All of those have to be equal to 0. Simplify. Reaction at A plus the reaction at B is equal to 1,000 pounds. That's as far as we can go with that equation because we have two variables that aren't defined. So the next step will be to sum the moments. So we'll use another equilibrium equation now, and we will sum the moments from a point A. And those have to be equal to 0 to be in equilibrium. And so the first moment we have is the reaction force at B. A moment is a force times a distance again. So the reaction force at B times 16 feet. Alright. We have this minus 500 pounds. That's going to be multiplied by 12 feet. We have another minus 500 pounds. And that one's going to be multiplied by 4 feet. And then we have the reaction at A, which is 0 feet. So all of that is equal to 0. Again, I ran out of room, so try to fit yours a little better than I did. We can simplify this now. The reaction at B times 16 feet simplify this. 12 times 500 and then 500 times 4. Gives us minus 8,000 foot-pounds. That is equal to 0. Reaction force at B times 16 feet equals 8,000 foot-pounds. We add the 8,000 to the other side, which makes reaction force at B equal to 8,000 foot-pounds divided by 16 feet. This gives us RB of what? 8,000 divided by 16 gives us 500 pounds. Go ahead and circle that. We can then plug that into our sum of our forces in the y direction. Reaction at A plus 500 pounds is equal to 1,000 pounds, which makes RA equal to 500 pounds. Okay, so once we have that, we can go ahead and draw our shear and moment diagrams. So the first one we'll draw is our shear diagram, and so I'll just sketch down below my free body diagram and put a point. This is going to be 500 pounds right here, representing 500 pounds. Here's our midpoint, and then we go down 500 pounds. And so in this case, the shear force, the slope of that is 0 until it gets to the first point, and then we have an undefined slope. It goes all the way over to the next slope on the other side, comes down to the bottom. So here's our shear diagram. This would be negative 500 pounds. And we can go ahead and hatch in the positive side. So that's the area we're going to solve for when we calculate the maximum moment. So I'll sketch my lines down. Put the maximum moment here. We're going to call that 0. And so now we'll calculate the max moment. The moment max, again, is equal to the area under shear diagram to left of center. So our moment is going to be equal to, in this case, it's going to be equal to £500, which we have right here, and that's over 4 feet. So that gives us a moment of 2,000 foot-pounds. And our moment diagram in this case is going to go up to that point, over, and down. We'll go ahead and label our max moment. is going to be 2,000 foot-pounds. So there's your example of a simple beam with two equal concentrated loads that are symmetrically spaced on the beam.